Okay, let's look at this circuit and talk a little bit about power in AC circuits. Okay, so we've got just a series RLC circuit. We've got it already in phasor domain. Notice this is voltages in magnitude and angle. All the resistor, inductor, capacitor are all given in ohms. And so these are Z's, JX's, right? And so everything's converted, and then it asks, what is V peak is the first thing it asks for. So just checking, do you remember RMS versus peak? So remember that RMS is, so VRMS is V peak over square root of 2. So V peak is just square root of 2 times VRMS. So it's going to be square root of 2. VRMS is the phasor voltage times 5. So 5 times square root of 2, 7.07. All right. B, what is Z total? So remember when impedances are in series, they add up just like resistors would add in series, right? So in series, they just add up. So Z total is just add these all up. Z total is 2 plus J.5 plus J, negative J.5. Let's do minus, not J5, J1.2. All right, so it's going to be 2 minus J 1.2 minus negative 1.2 plus 0.5 would be negative J.7. So that's going to be Z total. Okay. I. So we've kind of made this into a simplified circuit with just one impedance, Z total, just like we did with resistances. And so we can make our simplified circuit something like this. And so the source voltage is across Z total. And so we can just do Ohm's law, V equals IZ now, where the source voltage is across it. There's only one current, Z total. So we can get I of our loop, and it's the same I here, right, is equal to VS over Z total. VS, 5 at angle 0 degrees. Z total is 2 minus J.7. All right, so now what do we do with this kind of problem? Remember, it's easiest to divide complex numbers when they are in polar form. And so let's just go ahead and put the impedance in polar form. So we got 5 at angle 0, that's good. But what is Z in terms of magnitude and angle, right? So Z is, in terms of real and imaginary, is 2, X, the real part is 2, so what we would typically say is X is 2, and J actually is down. So it's over here, negative 0.7, right? And so when we have polar form, we need the magnitude, right? Magnitude of Z total, just the hypotenuse of the triangle, so it's going to be the square root of 2 squared plus 0.7 squared. And then the angle, we look at the angle here, we can call it theta. Theta is, well, tangent of theta is 0.7 over 2 with a negative sign on it, so it's going to be negative tan inverse 0.7 over 2. All right, this is the 2 here. Kind of looks like 2 is the hypotenuse, but 2 is the real part. Negative 0.7 is the imaginary point. So theta, then the angle. Yes, okay. So let's go ahead and calculate that a minute. Tan inverse of 0.7 divided by 2. 19.29 degrees. Okay, I guess let's just rewrite it. So I is still V sub S over Z total. Z total's angle now is negative 19.29 degrees. And its magnitude is square root of 2 squared plus 0.7 squared. 2.119, I guess we'll go with for now. right, so when you divide complex numbers, divide their magnitudes and subtract their angles. So 0 minus a minus 19 is going to be 0 plus 19.29, right? So 5 divided by 2.11. So our current then is 2.36 at an angle of 19.3 degrees. All right. That's part C. Got A, B, C. Part D, find the source apparent power. So the power of the source here, its voltage is given. Current we just found is the current of the whole thing. Everything has the same current. So the apparent power is the magnitude of S, right? It's like, which is the magnitude of I times the magnitude of V. So it's kind of like the old PIV, except for in the new AC world, we have to, if we're going to get P, we have to do cosine theta. So apparent power is just the magnitude of S, apparent power. All right, S as a complex number, we would say is a complex power, but that's not what they're asking for. All right, so magnitude of V, magnitude of I, we need a decimal point here. Magnitude of I is 2.36, and magnitude of V is 5. This is where it's important that it be an RMS. If these were peak values, we'd have to divide by square root of 2, but we've got RMS, and so we've got 2.36 is already in there times 5. 11.8. And the units for apparent power are volt amperes. This is amps times volts. So that's the magnitude of S. Okay. And that's the power of the source, because we took the voltage of the source times the current of the source. Just like with PIV, if you want the power of something, you take its own voltage and its own current. And you got to find what those are if they're not given. All right. E, the average source power. So that's P average. So we could do P as a function of time, but this is the average as a, just the average of the power over time. And so P average is kind of like PIV was in the DC circuit, but now it's magnitude of I, magnitude of V, cosine theta, where theta is angle of V minus angle of I, which is also the angle of Z, right? Because Z is V over I. If you divide complex numbers, you subtract their angle, so it's V's angle minus I's angle. So Z's angle is V minus I. Okay, so, and just as a side note, often cosine theta is called the power factor, PF, power factor. But well, let's keep on. Oh, that's what's going to be next. Okay, never mind. So let's put these in. So again, the magnitude of I was 2.36 amps. Magnitude of V was 5 volts. But now the angle, the impedance angle, or the angle between the voltage and the current is, do we not calculate? Yeah, is this, yeah, this is Z, is negative 19.29 degrees. The negative doesn't matter, but anyway, we'll go with it. 2.36 times 5 times cosine of 19.29. Cosine is an even function, so cosine of positive or cosine negative doesn't matter. P average equals 11.1 watts. So watts is volts times amps, but often with apparent power we call it volts times amps, just to keep track of, this is not the average power. Average power is watts, apparent power is volt amps. Okay. F, power factor, I just said, is cosine theta. It's also P over magnitude of S. Just looking at this equation, this IV is magnitude of S, magnitude of I to magnitude of V. So however we want to get the power factor. And so we could just say, we do cosine of 19.29. And it's always going to be something less than 1. right? Because cosine function doesn't get bigger than, or less than 1, bigger than negative 1, 0.944. And notice that this, like I was saying, the sign doesn't matter when we're calculating cosine, but it is kind of an interesting thing we need to know. And so whenever we have negative angle, that means that the power, we call it the power factor, is leading, because the current leads the voltage. It's like a capacitor, right? So PF is 0.944 leading. So when I ask you for a power factor, if it's not 1, then you need to tell me leading or lagging, because that tells you the sign of the current or at least the phase of the current with respect to the voltage. And so theta greater than 0, lagging. It's like an inductor. Theta less than 0, leading. Current leads the voltage like a capacitor. Right, and we can see that happened because our capacitor in size of ohms was bigger than our inductor, so it acts mostly like a capacitor. So it has a leading power factor. Okay, current leads the voltage. Part G. What is P average of the capacitor? P average for the capacitor. So this was of the source. We were looking at, these were all of the source, right? Because we're taking the voltage of the source everywhere. But now it's asking about the capacitor. So now we need to look at the voltage of the capacitor versus the current of the capacitor, or it's a little bit of a trick question, but let's just kind of do this. So it's going to be magnitude of I, same I for everything, times magnitude of V of the capacitor only now, times cosine theta of the capacitor, right? So theta is the angle, the voltage angle between the voltage of the capacitor and the current. And with capacitor, it's also the impedance angle, right? Z sub C is magnitude of Z at angle theta sub C. And so what is the angle of a capacitor? It's always got this negative J on it. So theta sub C is always negative 90 degrees. And so what's cosine of negative 90 degrees? 0. Right? So P average for a capacitor, any capacitor, if it's ideal capacitor, is 0. Right? Capacitors don't use up, So P average, I times VC, cosine theta C for a capacitor, the impedance angle is always negative 90. And so it's leading, but the power factor is 0 because the power is 0, because cosine of 90 is 0. And so capacitors and inductors, if it's just the pure capacitor or just a pure inductor with no resistor in with it, it's going to have 0 real power, 0 average power, right? Because capacitors and inductors, they alternate the energy. They pass energy back and forth. They don't dissipate power. They don't dissipate energy, right? So they will have 0 average power. It comes in, and then it goes back out and comes back in, and so the average is 0. All right, let's stop there.